Rajesh, shall we start at 6?
Yes, we'll start.
Okay, so we'll start on time. Okay, let the participants join. Okay. Yeah, you
Okay.
can start. Yeah.
A very good evening to all. Welcome to the day two of this ATAL FDP on AI-driven innovations, transforming core engineering disciplines. For today's session three, we have an esteemed speaker, Dr. Muddu Madakyaru. I'll take this opportunity to introduce Dr. Muddu. He's a professor in the Department of Chemical Engineering, Manipal Institute of Technology, Manipal Academy of Higher Education, Manipal, which is in Karnataka. He received the BE degree in chemical engineering from RBC College, the MTech degree from chemical plant design from NIT Karnataka, and PhD in process control from IIT Bombay. And he was a postdoctoral researcher with Texas University, Doha, for 4 years. And he is the co-author of book entitled Statistical Process Monitoring Using Advanced Data-Driven and Deep Learning Approaches, Theory and Practical Application. This is the book title of this, which is published by Elsevier. And Dr. Muddu has published his work in the renowned journals and major conference proceedings. His research interest includes advanced process control, including system identification, fault detection and diagnosis, AI, and deep learning. With this brief introduction, I take great pleasure in calling Dr. Muddu, sir. Sir, please, session is yours.
Thank you so much, Dr. Rajesh. Also, I am very thankful to SSN for providing me this opportunity to share my views on this, particularly process monitoring, how this data-driven modeling can be used in process monitoring, basically. So, with that note, let me straight away start. So, if I want to look at this AI application in chemical engineering, basically the publication will give us an idea about number of applications evolved over a decade, how actually the increase. That's give a clear idea about AI application in chemical engineering field. So when you say AI, is nothing but any technique that enables the computers to mimic human intelligence, but that's nothing but a kind of a layman language, you can say that. And also we see that the Venn diagram I show that machine learning and deep learning is also a subset of AI. Sometimes also we say that AI is a subset of machine learning, deep learning is a subset of machine learning, all those things. Now look at this, how actually this AI application in chemical engineering evolved. For example, in the year 1970, 75 onwards, there is an early excitement actually of AI in chemical engineering. Some people, great people have worked on that. But it was like they were not able to do much work on that due to some reasons, and it's a very simple network and all those things. They failed to, excitement was there. So you can say that the first winter, it has actually happened in this direction. And then around 1980, there's a second excitement started around 90. So that time there is a backpropagation algorithm, they could solve it, and the simple network could be come up with that, and then some of the machine learning algorithm also came up in the same time. But in the meantime, the chemical engineers also started applying the AI in our process industries. So even though it is other domains, AI was well established, but chemical engineers actually lagged almost 1 decade in that. But around 2005, 2010 onwards, so a lot of computing power, which you have got it, and then very good algorithm also came up, and then AI applications zoomed very much. If you look at the graph here, you can clearly see that the number of applications around this, after 1970, 75 onwards, slowly increasing. Now, if you look at this, around this trend, around 2015 onwards, 2015 or 2010 onwards, the number of publications in chemical engineering, AI publication in chemical engineering increased drastically. I don't know whether it drops down or it goes a plateau or it's keep increasing in this. We'll have to see how it's going to happen. Okay. Now, this is how this AI actually in chemical engineering is evolved. So this gives an idea about how this actually happened based on the number of applications. Now let's look into this broad application of AI in chemical engineering, or I can say that's process system engineering. It's not that we have been doing a predictions using other analytical models as well as, for example, Navier-Stokes equation is one of the powerful equations which have been used to predict some properties as well, some flow properties. But then there is issues that you don't get the analytical solutions and all those things. So there is a computing power also is required more. Then came up with this because of this. So why don't you look into the data-driven type? So huge amount of data is actually started getting it. And then, so once you started the data, so the main, before getting into the AI itself, so you'll have to look into the data carefully. That means once you collect the data is having both information as well as a noise. That means unwanted information. So that noise has to be eliminated first. And also there is something called a redundancy among the variables. So you'll be collecting so many variables, but some of the variables having no role to play in developing a model. So such variables has to be removed before even getting into the AI application of AI in this. So that's what I mean. So if you look at this particular slide, so the data rectification comes first. So once you collect the data, extract the meaningful features from the raw data through eliminating the redundancy as well as the noise. So whenever the data comes, it always comes with the noisy. That means, so the noisy has to be removed first. So then once you're done with that, the purified data, the curation of the data is done, then useful features have been selected. Then other broad four applications, which I have marked here on the slide. One is the process. First, let me start with the process optimization. What exactly you do? AI. What is the role of AI in process optimization? For example, we are optimizing the process conditions. So the design is based, process equipment design is based on the steady state operating conditions we do. And then we set the operating conditions. What is the operating condition? Optimal operating conditions. But over a time, so these operating conditions also might change due to some reasons, because some of the equipment may not perform well in 100% efficiency. So the operating condition also you may have to change. That's one thing. Another one is that in the case of a batch reactor, for example, you will not be conducting at steady state conditions. So this is operation will not be at steady state conditions. You will be following some profile. So in such a case, how do I get this profile as and when the data comes? That means you keep collecting the data. That means the past data is with you, and based on the information of this past data, that means history of the process, I can update the process parameters or process conditions itself, so that I can operate the process in an optimal way. So that is what actually is AI can play a big role in this process optimization as well. When it comes to the process control, all of us studied this particular, of course, process optimization course is not there in our chemical engineering curriculum, but unfortunately, I think we should include, if you are really working on, you plan to introduce some AI course in our undergraduate course, we should incorporate optimization course so that you get a better idea about that, how it actually works. Now, application of AI in a process control. So we study in a first course in process control or process dynamics and control. So how do you track the controlled variable using fixed PI control or PID control, right? So that means the structure of the controller is fixed and the tuned at a fixed value. So that means it'll be over time. So the performance of these controllers is going to deteriorate due to some reasons, right? So that means we need to update these process parameters or control parameters as and when the process condition keeps changes, or to keep the process control variable or control variable at a desired value, you may have to update the control parameters at optimal value. So for this also you can use it, AI can be used it, because these days people are talking about data-driven design of a controllers and all this. This is the same thing basically, data-driven design of a controllers. When it comes to, this is all about the process control point of view. And when it comes to predictive modeling, yes, we extensively use this model to predict what is the outcome of the process. For example, in the case of a distillation column, if I want to predict what is the composition or top compositions or water compositions, I can make use of some model to predict that, right? So that is how it is actually the AI model can play a big role. And now, what is the use of this predicting predicting the top composition and distillate composition, so that you will, well in advance, you know what's going to happen to the plant, so that you can take a corrective actions well in advance. So this is based on the MPC, that's the model predictive control, that's where you use it. And coming to this, next one is the process monitoring. This plays a very important role in a big plant. Basically, you have a huge number of units, large number of units, as well as huge number of sensors and actuators operating continuously for 24 hours into 7. Right. These sensors basically giving out the data. So that means we need to monitor these sensors carefully. So whether these data are giving the right result, right values, or some of the actuators, let's say some of the actuators, are they working properly? Is there any fault in the actuators? Because these all work in a continuous loop or a closed loop. Now, if actuators having some fault, let's say stuck, then it's a big issue. Even though your controller is working fine, that gives out a nice controller output, controller move, but that goes to the plant, but your actuator is not even operating. That means, well in advance, you should know, yes, there's a fault in the actuator. As well as case of a sensors, because sensors gives an idea about what exactly happens, because sensor gives out the data is having some lot of information. So using that information, you can extract what is actually happening. Now, if there is a sensor failure, so that is again is a problem, especially with respect to the controller design. Now, if the sensor is a fail and the failed sensor value which goes to the controller, so the controller will start taking action based on that value. So that leads to again disasters. So that means continuous monitoring of any plant is required. So that is a broad application of this. AI can play a big role in this monitoring. Okay. The next, which I'll be, okay. So are you able to see my slide? Because there are some hiccups here. I could. Dr. Rajesh, are you able to see?
Yes, sir. We are able to see for slide
number 4.
Yes.
Yes. Now, what is AI? AI is nothing but a discovery and purposeful utilizations or exploitation of meaningful patterns and information in the data. That means basically you're going to use data itself. So using this data, you're trying to extract meaningful patterns and informations, that further information can be used for modeling and predictions. I was given an example. I just again and again I give the same example. Design of a controllers. So you can see this basically. So feedback controllers design. All of us familiar with this particular block. Actually, in the faster scale, you have been doing this. You have been effectively utilizing the data for navigating the plant, basically. So, for example, the sampling time is, let's say, 5 seconds or 10 seconds. Every 5 seconds, you're measuring the control variable, and then the controller start taking action and sending the controller mode to the final control element, and in turn, it operates a manipulated variable. That's what we do in a very faster scale. But that's one of the very crude approach we follow. But what else more than that can you do? Because the huge number of data, because why do you get a huge number of data? Because nowadays you install more number of sensors so that you can get more information. The new generation approaches mainly focus on huge amount of data. Again, you have to be very careful. Data comes with a noisy. So that means you have to extract the information from the data. Only the useful features has to be taken into, and the noise has to be removed from that. That information has to be transformed to the knowledge. And that is the knowledge, and then we should be able to take the right decisions. So that means that's the wisdom, what I mean. Okay. Now, so after this, I'll be talking about this. What are the three major links in the AML? So that's also called as ABCs of machine learning or AA. As I said, the data plays an important role. As a chemical engineer, you have been collecting the data in lab scale, pilot scale, and through modeling or through simulations, right? Huge amount of data will be collecting it. And this also can be collected through simulation because, which I don't want to do the experiments, and then simulation can be carried out, and then huge amount of data can be used. So this data comes with some kind of a, as I said, it's a noise. So that means you need to extract useful features as well as useful information by excluding the noise part in this. Okay. Now, this data set, once you collect the data set, then before sending to the model development, I'm going to split into some kind of a three parts. Let's say training data set and validation data set and test data set. Basically, when I say training data set, we usually use it for training the model, basically. So that means you have you have already fixed a model, what kind of model you want, and you train that model and get the model. And then simultaneously you do validation using validation set to just generalize the model. And then use a testing data set, which is not seen by the model, just to find the efficacy of the model. We usually testing data set will be used because this testing data set, which is not seen by the model. So that means exact efficacy of the model will be known only through the testing data set. So the range of how do you go to split it, training, validation set, and data set will be. Now, once the data is collected and the data curation is done because useful information is got from the data, so then how do you go to represent that? So when your data is collected, it comes in a numbers, it comes in a text, it comes in a images, it comes in a different form. So we'll have to use it, how we are going to use it for developing a model. So that means how we're going to select which features to be important to us. There are some techniques, machine learning algorithm, which actually tells us that the automatic algorithm, which tells us that which features plays important role. Or statistical tool also can be used to find out which variable plays important role to come up with a model, good model. Now, as a chemical engineer, there are some issues with respect to, because we always deal with the molecules and the chemical reactions. So how do you represent these data set? That means it is not a straightforward to represent a molecules. So as well as the chemical reactions, I find it much more difficult to represent the data. So there are some work is going on how to represent the molecules with a smile and full form I don't remember, but anyway, that a smile structure can be used to, 3D structure can be used to represent the diagram, but it's not in a full form. But still work is going on to represent the molecules and then this chemical reactions. So once the representation is done, then it's simply that you're coming up with a development model, developing a model using some known structure. In this case, which I shown is some kind of a deep learning neural networks can be used. Basically, this can be, you can think about based on the strategy, what you want to have, whether you want to predictions, whether you want to have a classification, whether you want to have a just gather the informations or patterns in the data. So based on that, you can think about what kind of a modeling strategy you can develop. And basically the purpose, sometimes you based on the application also be classified as that supervised learning and unsupervised learning. That I'll be talking in detail later. So the main message which from this talk, which from so far, that's what I think. There is a shift in the way we make a decision. That means we'll have to listen carefully to your data. They interpret the signals into meaningful informations, build a knowledge using informations. You are a safe and improved optimal operating policies. So that means you should be a little careful. So don't load it with too much of data. So that means data which is not having any information, that not going to serve the purpose. So that means while collecting the data also very important. So you might do some experiment in the lab scale, but the data is not having any useful information. That data will not have any, will not help us in developing a AI model. And that also might lead to too much of data might lead to your computation power. So it might require more computation power. So once you have the data, translate into actionable information. That's what we want. Now, so there are different approaches. You can, how do you extract the knowledge, or how do you refine the existing methods? So there are two ways actually. One is that the models, I can come up with the models and then supplement it with the measurements. So when you say modeling, and there is always a mismatch between the model and the actual plant. What is a model? Model is nothing but the approximation of the real system. So you may come up with a model using a set of mathematical equations to represent the real system. Right. You might go for a simple systems or a complicated, simple model to all the complicated model systems. So as you go complex model, you may end up with the problems as well, because the number of parameters to be estimated more, and then solution strategy you have to look for it, all those things. There are some methods which I'm going to suggest you. So as I said, there's a models which will have a mismatch with the real systems, and then also the measurement which actually can be incorporated in the model so that you can improve over a time. But now measurement comes with the noise. So how do you deal with this? So that means
Any issues, sir?
I think we lost him.
I think net connectivity has gone, I think.
Yeah, I will call.
Yeah.
Maybe he'll rejoin.
We will rejoin.
Dear participants, please be online. We lost the contact with Muddu. He will be rejoining in a few minutes.
hello, Rajesh, can you give me access? Can you give me access now
Yeah, we'll give,
to
sir.
share the
Yeah,
the
sure,
slide?
sure. Yeah.
Please check, sir, now.
Yeah, I got it.
We are able to see your screen, sir. You can present it, I think.
You are able to see my screen?
Yeah.
Yes, sir.
Desktop?
Desktop is, yeah.
Yes, yes.
Okay.
In slide number 7, we stopped, I guess.
Yeah. Yeah. This is a slide.
Okay.
Which is, yeah.
Yeah. We're good to go.
Yeah. So I was telling that if I want to extract the knowledge of the process, there are two ways you can do that. One through models and then supplement with the measurements. And I was telling that the model always, when you develop a model, it always comes with a mismatch and measurement comes with a noise. So whenever you have this kind of a scenario, you can always think about the solutions which is already exist in the literature or some industries already using it in this. Accurate model, when you have accurate model, that means the accurate model, it actually comes from the white box model or a first principle model based model. And the measurement comes with a noisy. In such a case, you can always use a technique called data reconciliation, which is used in industry as well. Okay. And that's why I was telling when you have accurate model, add a simple model, accurate model, which is developed through first principle approach or mechanistic model, and the measurement comes with the noisy. So data reconciliation. When you have a noisy model, there are some noisy. If I want to capture the noise, you can always develop a noisy model and a noisy measurement. Then something called estimation and filtering technique can be used to counter that as well. When model partially known and noise measurement, you can always develop a gray box modeling and adaptations. So what do you mean by gray box model? That means part of the model is developed through first principle approach and part of this parameters actually obtained through some data driven approach. So that means you're going to get a gray box model. And then as and when the data comes, and then you can fine tune the model through adaptation as well. And then if the system is very complex and poorly known, so that means too much of uncertainty in the model and too much of a noise in the data set. And then there's the only way is that you can come up with the black box modeling, or you can make use of multivariate statistics, and then artificial neural networks or fuzzy other AI tools can be incorporated in this. Is it okay? Dr. Rajesh, it's fine?
Yes, sir, it is fine. You can go ahead.
Okay. So that's just one just a picture which is actually says that how actually our linear regression can be used to find out what is the amount of income you get based on the number of years of higher education. Simple model based on the data collected. It actually basically the collected data and then trying to come up with a model which gives then after that, once the model is developed, then we don't need these data set. You just find out the income using this simple regression methods. You can use machine learning technique can be used this one. And also you can come up with some complicated model, also machine learning model also for this case. For example, you have something called as artificial neural networks. It's also the more number of hidden layers in the neural networks. That's why it's a deep neural networks. So the more number of hidden layers and more number of nodes in this case, you can always think about coming up with this kind of model approach as well. So basically, when you think about this, how humans learn, so basically how the knowledge transfer takes place in this our academic system itself, you can see that since our students get knowledge through attending a lecture. It's not only the one source by attending the lecture they get the transfer, but by doing additional work also they'll be able to get that. Then there's some kind of a feedback. They go back and then something they study and then come back and then ask the question with the tutor and then they'll be able to clarify that doubt. And then along with that, other examinations also gives them some additional inputs so that you'll be able to transfer knowledge. That's all. This basically all this is the features, basically inputs. Basically, similarly, how we learned the cycling during our childhood days, you can think about it. In the first go, nobody learned the cycling. Basically, the first time when they do that, they just fall down, right? So we experienced it. So the second time, he'll be careful. He or she'll be careful doing that. So he'll be learning from those mistakes what he has done in the first time. So that means machine learning is basically you keep training based on as and when the new data comes, so that or AI you can think about that. So that means why machine learning is required, because if the system is too complex or difficult to understand or difficult to construct some kind of a model which required a domain knowledge as well as the detailed skills is required, then it is difficult to develop or it may be time consuming. And in such a case, we'll be using a machine learning method to do this. So the real world applications you can think about as extensively used in computational biology and medical diagnosis, because now these days AI-driven medical instruments are coming little dangerous, but it's in the market now, AI-driven medical equipment, because the doctor don't have to worry about much looking at the report, and instrument itself going to suggest what the medicine for the patient, given patient. So this basically AI model is already there, and the patient data is already stored in that model is developed, and then directly diagnosing it. And extensively used in the case of process monitoring, because as I said, my interest area is the fault detection, diagnosis, and process monitoring side. So many people work in this area as well. So the new algorithm, they try to use it for fault detection and diagnosis as well. And another application, strong application, coming up with the soft sensor and application, the process control or feedback control design. Now, the advantage of the soft sensor is that, for example, you can think about the distillation column. In that case, we have a controlled variable, right? Controlled variable you can think about as a quality variable. Quality variable, in the case of a distillation column, it is nothing but the top composition or a bottom composition or a composition. Now, if I want to control the top composition or XD or XB in the technical terms, so we need to measure it. We need to measure those variables so that I can take actions based on the difference in the set point or a target value. Now, if the value itself is not there, how am I going to take the actions? That means I don't want to invest so much of money to measure online these process variables. Then the soft sensor comes in play, important role, because I can come up with a kind of a software-based sensor, which is nothing but the model is developed based on the input data and output data, and based on the data, and then simply put it in the software, and which predict the controlled variable, and then normal feedback control strategy can be used. So basically, soft sensor basically estimate the controlled variable, and then you'll be able to take the control action in the case of process control. That's one application, strong application of process control. As well as the manufacturing side, when do you want to go for a shutdown, and all those things can be used for using AI approach based on the data. How is the functioning of each instruments and each machines, and what is the manpower requirement, what is the existing manpower requirement. Based on that, you can always go for a predictive maintenance so that you can major shutdown can be avoided in this. So the major application also comes in this natural language processing, because that is where the computer science people are working on this. You can think about ChatGPT, all those things, AI-driven natural language, lingual processing. And other areas, also non-chemical engineering areas, image processing and computer vision, motion detection and object detection can be used extensively in this. So that's a non-chemical engineering applications, but there are a lot of progress in that area as well. And now, why suddenly this AI-driven or chemical engineering shown some interest in this? Because one reason is that huge amount of data is available with us because of the data acquisition systems, and especially with the advent of internet, right? And also the increased computation power, because we also need a computation power to do that. So one example I can think about is that adaptive control strategy could not be implemented in any plant around 20 years back or 25 years back, because even though adaptive control strategy or adaptive MPC control strategy was there,
on the literature, but you could not implement because we didn't have the computation power. Only it's a small scale you could implement it, but in a larger scale we could not implement because within a span of 5 seconds you'll have to compute all the control modes and adapt a model. That was a big challenge. Now, yes, it is possible because of the availability of the computing powers. And the next also credit goes to very powerful algorithm as and supported with theory developed by researchers, which goes there. And also the increasing support from the industry because now industry also is accepting this and will be having some. So, and another last one is that open source software is available because now let's say Python and all those things can be used anybody, and then so everybody started using this. So you don't have to pay for it. Okay. So basically, how machine learning works, basically that's it's not exhaustive classification. Basically, I just simplified it because there's one more class which is a reinforcement learning. I just kept it. And used the two types of techniques. One is that supervised learning, other one is unsupervised learning. So when you say supervised learning, we take both the input and output data. So that means we call it as a labeled data. So we use a labeled data. That means labeled data when it says that given input, what is the response variable, what is the response, or what is the target value, which is given to us. So you can say that X and Y is given to us. That's a labeled data. And which is used for extensively for classification and regressions, the classification and regression. So classification, it's basically the predicting the discrete values, and the regression is used for predicting the continuous values. And another technique which comes from the machine learning is unsupervised learning. So basically use unlabeled data. In this case, we don't distinguish between input and output. We use just whatever the data we get and try to interpret the data or what is the pattern existing in the data set. So that's a broad two machine learning algorithms which is available in the literature. That's one is unsupervised learning, another one is a supervised learning. So best example, you can think about the clustering example for unsupervised learning because you want to find the patterns, what is the patterns in the data. And also sometimes we use first you perform the unsupervised learning and then we go for supervised learning. That's also possible because unsupervised learning also used for dimension reductions and then noise reductions and all those techniques also used. A non-exhaustive list of useful algorithms you can see in this particular slide. It has a classified supervised learning versus unsupervised learning. So there's one more class, reinforcement learning. I have not added here. So under the class of supervised learning, it's basically classification and regressions. As I said, classification used to find out the discrete outputs or response variable. Regressions is used for a continuous variable. Okay, so under this class classification, we have SEM and logistic regression, naive-Bayes, k-nearest neighbors, random forest. Similarly, in the case of regressions, we have linear regressions, ensemble methods, and neural networks. Similarly, unsupervised learning algorithms, when it uses unlabeled data, tries to discover the patterns basically. So you can use it for a clustering as well as you can use it for a visualization, because when you get a multi-dimensional data, I want to see how actually the data looks like. So that means you'll have to reduce the dimension and then see. So that means well-established techniques, which maybe you can think about it, the PCA is 100 years old, the technique which is still exists and still it's very powerful techniques in the machine learning. It's a domain. PCA, principal component analysis, and TSNE, and then independent component analysis also can be used for that. And this also can be used for dimension reduction because when you say dimension reduction, because we are collecting a huge number of variables at a different sampling rate, and then that's the dimensions of this data set is a huge. Let's say 1,000 variables you are collecting at every 5 seconds, every 10 seconds, and then collected for 1 month. And this dimension has to be reduced before you are sending it to AI model or a machine learning model, because this contains a lot of noise as well. So that means when you reduce the dimensions, you'll be reducing the computation load required for the computer as well. And then dealing with the less low dimensions is much easier than high dimensions. So that's one of the reasons we usually perform this dimension reductions. The advantage of using a dimension reduction technique is that in that process, we also reduce the noise content in the data as well. So you have to be a little careful because you should not lose information while using the dimension reduction techniques. And then unsupervised learning method also used for anomaly detection or fault detection, same technique which I use in the case study, which I'm going to show here. And so there are some which I show in this slide. Basically, this supervised learning, how this classification is done, how the regression is done. Basically, you collect this data set. So, for example, the red raw data, which is a mixture of different colors and different shapes, and you can later you can interpret the data and then send it to the algorithm, and the data processing is done. Then after that, you will be able to classify which shape and which color. That's basically the classification techniques performed this way, right? So this also, the classification techniques also can be used for whether your sensor is healthy or not, emails are genuine or spam, whether the tumor is a cancerous or benign. So medical applications which are given. So basically, you're given the input data, you just categorize it. Other applications, non-chemical engineering applications, medical imaging, speech recognition, and other credit scoring. So basically, when you have a classification problems, you need to have a balanced data set because a good amount of faulty data and non-faulty data, or healthy data and non-healthy data is required to your model to perform very well. Whereas in the case of regression techniques, basically, again, the data set which is shown is X is input, Y is output. We need to have the labeled data, and then dot is basically data set, and then you're coming up with the regression model, and then that's a regression model can be used for predicting what is the yield in some process based on the temperature measurement. If X has to be the temperature or Y is your quality, then you can use always whenever given temperature, unknown temperature, you can predict what is the quality of that. So you can basically, given X, you can find out a Y. So you have been doing this in a graph, but you can always do it in this. So thing is that you may not have one variable, one X, you may have multiple X because X1, X2, X3, all the way up to go up to Xn. So how you're going to develop such a model. Similarly, unsupervised learning process, trying to find the hidden patterns. Basically, given this data set, basically you try to make a cluster, this particular data set, and belongs to this. So basically one which is having a similar properties, which actually cluster together, and you'll be able to visualize it, as well as also you'll be able to come up with some kind of what is the patterns within the data set will be can be used. There are many techniques which I given the place. Now, slowly I'll get into the process monitoring case. So quickly I'll go that because we have process control system, sensors, and then huge amount of data set coming in there, raw sensor data, then has to be processed with the feature selections, and then learning task happens with the machine learning, and then this can be used for predictions. Once the prediction is done, you'll be using the residue information, whether there is any fault in the sensor. That's it. So I skip this. Basically, this is what this is a slide which says that how you're going to collect the data from the lab scale to the plant scale. Each step plays important role. Each step plays important role, especially for chemical engineers, because we collect the data in the lab scale that could be related to what is the purity, what is the efficiency. In the pilot scale, what is the operating condition supposed to maintain in the plant, and both inter-stage and interstage has to be checked. For example, in the case of reaction analysis using machine learning strategies, we need a lot of data from the different sources. What is the product properties? What is the compound data? What is the reaction data? What is the molecular structure? Everything we might require if you want to come up with the AI-driven model, basically. So now, before I getting into the basic machine learning or process monitoring case studies, I just some tips applying for machine learning, because it's very important. Diagnostic steps plays important role. If you end up with anything wrong in the predictions or a classification, how do I diagnose my model or a model or machine learning model? So basically, I'm talking about how do I debug the learning algorithm. Suppose you have implemented a kind of a regularized linear regression to predict distillate composition in a distillate. That means basically you're predicting the distillate composition in a distillate. Now, this is your cost function basically. So this is your cost functions, or you want to minimize this cost function. This is a cost function defined as a mathematical equation. Don't worry. However, when you test your model for a new data set, you find that it makes unacceptably large errors in the prediction. Basically, during the training stage, your model was good, but when you use it for testing your model, you found that a lot of errors in what should be done. So this problem comes is that the answers are that, can you get a more training examples? Can I get a try smaller set of features? That means you are taking a large number of features. And can I reduce the number of features? How am I going to reduce the features? Or try getting additional features, or try adding a polynomial features, or try decreasing the lambda. That's a regularized parameter, or try increasing the lambda. So basically, this equation tells us that this is a cost function used to find out the your model, but now you found that your model is not performing well for a new data set. Now, what should be the problem? So where exactly I can put this? Now, how do you evaluate the model? Basically, as I said in the beginning of this, when you collect the data, let's say in this case, you have a labeled data, we have X and we have Y, and split into three parts. One is the training data set. 60% of the data can be used for training, and later 20% can be used for cross validations, and later 20% used for testing the data set. So that's how we're going to split into that. Sorry. Now, so you can always so you can always find the training error, cross-validation error, and the testing error. So this particular equation is a familiar tool that you might have come across this particular equation. There is some squared error, but only thing is I added divided by 2 times of m. That's no problems because anyway, it's a further reductions value. So that's particularly, you don't have to do 2 here. You don't have to. Okay. So basically, training error, basically you get when developing the model. The cross-validation error you're going to get when you have used the 20% of the data, the model, and then find out the error. Testing error, you're going to get that it is not seen by the model itself. So you're giving only the input data of the testing data set, and then finding out the y hat, and then finding out that x theta of xi and y. So this difference is nothing but error, and you're going to find out the j-test error. So now, if you plot this cross-validation error, you're going to look like this basically. So you can think about the model complexity on a x-axis, and then y-axis you can think about this error. So as you see this cross-validation error is very high when the model is a simple. Yes, it is because model is a simple. You're not representing the real system properly. So as you increase the model complexity, that means the structure of the model increases, or complexity of the model increases, the cross-validation start decreasing, and after some time it started increasing. So that means you'll have to be very careful where exactly this.
Sir,
Yes.
one question in the chat. What is M here?
M is the number of samples, basically number of data points.
Okay.
Okay, so let me clarify, because h theta of xi is nothing but you can think about the y hat. Y hat, because this is a model. H theta of x is nothing but I represent the model. That's a hypothesis, or I can think about as a model. So this is basically y hat for a given cross-validation data set. H theta of x, in the case of training, it is a 60% of the data set, given input, and then find out the y, that's a y hat, minus y. So I varies from 1 to m, that is number of samples. So in this case, cross-validation error, number of samples, cross-validation set data. In the case of a testing data set, it is a testing. Sorry, I'm not able to see the chat. So I have to minimize it. Then only I'll be able to see it. So if there is any question comes, please let me know, Dr. Rajesh.
Sure, sir.
Okay. So now, basically what I'm trying to say is that whether your model developed or a machine learning model algorithm is suffering from a high bias or high variance, I just wanted to see. Now, what I'm doing is that I've taken a simple model. You can see that, very simple model with I have the 4 data points, the first plot, second plot, third plot. If you see this, very simple model, theta naught plus theta 1x. So basically, it's not able to fit the data very well. It actually suffers from high bias, basically. So that's because of the simple model, it's not able to fit. Now, if you look at the last graph in the screen, I've taken a little complex model. You can think about a complex model as a 4th order polynomial model I've taken, and it's going to pass through all the data points exactly, right? And now, what happened is that, but in the training stage, yes, it's going to pass through this, all the data points, fine. For the training data points, it's going to fit very well. But when I give a new data, so it's going to suffer. It's not going to give good prediction because it suffers from the high variance. Because more number of parameters, you have less number of data points that leads to this. But look at this, the middle one, it's just right fit, right? So whenever this kind of issues, you'll have to classify clearly whether it's a model is suffering from high variance or high bias. So let's go further. See, now look at this. I've taken the first plot and the third plot separately. Now, what I've done is that we have a training error on the left side. That means I calculate the training error. So y hat minus y train, and then which is suffer from high bias, right? That's only when you have a simple model. Let's say when a simple model. When you take a complex model, this also the same algorithm. It also suffers from high variance. Now let's look at this. What's going to happen? So that is now. If you look at this one, the training errors it start decreasing as you increase the modeling complexity. That's a blue line indicates that as you initially the training error will be very high. As I increase the model complexity, the training error start decreasing and it might go to even 0 because if you increase the complexity, that's what happens here. Now, if you look at the cross-validation error, this is the first blue line indicates the training error and the bowl-shaped curve indicates the cross-validation error. Now, here what happens is when there is a very simple model, it's not going to fit the data very well. So you'll have a very high training error as well as the cross-validation error. As we increase the model complexity, the cross-validation error start decreasing, and after some time, so model cross-validation error also start increasing because you have more number of parameters to be estimated, and that leads to a with suffer from high variance. Okay, so this is a plot which just suppose I want to say if you want to classify your algorithm whether it suffer from bias or variance, so we'll have a training error will have a very high as well as the cross validation is very high. Then you can classify as that which is suffer from bias. And if you want to classify that particular model, which says that high variance or overfit, it suffers from overfit, commonly used word in a machine learning, or the overfit or underfit, which says that training error is very low and cross validation is very high. Then I can come up with this model. And similarly, when you want to deal with some kind of overfit, so one techniques usually we follow is the regulation techniques, which is well established in the linear algebra as well. If you have a matrix, which is a ill condition matrix, if you want to regularize, if you want to condition it, we use a regularization parameter as well. The same technique, somewhat the same techniques which is adopted here. You can think about a linear regression with the regulations. Now I can consider the model as this 4th order polynomial model. That is the cost function which I defined as this, right, with the regulation parameter lambda. Now, if I select the large, now the problem is that how do I select the parameters? How do I select the regularizing parameters in this case? Do I select the large lambda? Do I select the small lambda? So what's going to happen? So now let's say we have a selected the large lambda. That means let's say lambda is equal to 1000. Now if you look at this particular j theta, so when you select the 1000, this kills all the parameters, let's say theta 1, theta 2, theta 3, theta 4, because this particular regulation parameter which starts from 1, j is equal to 1, that means theta 1. It starts from theta 1 all the way go up to theta n. That's the number of parameters. Now it is not, we are not penalizing the initial value, that's a theta naught. So now this term is actually nothing but y hat minus y square plus lambda and squared parameters and sum it up. Now, if you select the large values, let's say 10,000, you're going to end up with a model as h theta of h is equal to just theta naught. And all this theta 1, theta 2, it gets killed and it becomes almost 0. That means you'll not be able to use all the features at all. So that's going to happen. That's what you're going to have, this kind of a model. That means, similarly, if you look at the last plot, when you select the very small values of lambda, so that means you're giving all importance to all the features. That means whether you require features or not. So this is the now here the solution basically. So now you're taken all the features to develop a machine learning algorithm. Now you don't have the technique to select which feature to be selected for developing a machine learning algorithm. Now you can use your lambda as one of the tuning parameters to select. If you select the small lambda, all the features will be selected and that leads to overfit. Now, if you select the intermediate lambda, then there's a chance that you will end up with a good model because it might be giving a weightage to each features, but it may not be giving a weightage to weightage to all the features. And now choosing a parameter is a little.
I have one question.
Yes.
This
Yes,
regularization parameter is something like correction number or correction value or correction function. If so, how to decide which functions to be put?
It is not exactly the correction. This is a parameter which is actually kind of is the trial and error method only allowed to choose it. There is no straight method I can come up with. The lambda is this because each data set is a different, right? Each data set for a given process is a different. So that means each features plays important role in predicting the response variable or classifications. That means how I'm going to choose this data, it's only by trial and error methods only. That's the next step which I'm going to discuss. That is one. Okay. So basically, the lambda, if you want to select, best way is that you just make a grid of lambda and come up with the different values of lambda and perform this model, and then perform the model and calculate the cross-validation error, and one which gives the minimum cross-validation error for a lambda, which can be selected as the best lambda. That's the only way to do that. Okay. So I hope that is clear. It's a computation too much. Yes, that's a worth spending time because you don't have to worry about later. And now that's just a graph which says that which you want to find out your model, whether it's a suffer from high variance or high bias. Lambda can be used, the right fit can be used. X-axis is actually the lambda. That means you're going to make a different grade. The error is calculated. And we have plotted the training error as well as the cross-validation error. When there is a lambda is a very small value, so you're going to have a very high cross-validation error, very less training error. So that means immediately you can say that this is not the value supposed to use it. But similarly, when you use high value, so we'll have a very large training error because it's not going to fit the data well itself. When you take a large lambda, it's going to kill all the parameters, and that's fit doesn't help. Similarly, the cross-validation error also is going to be high. This is where this comes. And the right value fit could be where the minimum comes, the cross-validation error, where the minimum lambda can be fixed. So that's the only way is that. So that is some of this thing. I just keep this. And that's a machine learning algorithm error matrices. So once you're done with your techniques, basically, so which could be classifications, you come up with a different machine learning algorithm. You want to find the efficacy of the machine learning, your model. The best way is that there are different matrices, which can be used this. So this also called as confusion matrix in the computer science language. So basically, this confusion matrix, what it says, the 2 by 2 matrix. Basically, we have actual class. Let's say we have an actual value, it's a 1, and predicted by the model, it is a 1. Then you can say the true positive, that's a TP. Predicted the model is 1, but the actual value is a 0. That's basically we say it is a class as a false positive. Basically, it's not actually. It's not only model is predicted as a 1, but actually it is a 0. Similarly, you can classify as a false negative and a true negative. So the predicted class is 0, but the actual value, because you get a label data, right? So you can always evaluate this your machine learning model, and actual class is a 1, then it is called as a false negative. Predicted class is 0 and actual class is 0. It's actually called as a true negative. And basically, when you develop a model, machine learning model, we expect the true positive should be high and true negative should be high. That's you don't want a false positive and a false negative. This might have come across in during the COVID time. So testing, they say that it's too much of false negative, too much of false positive. So that is what actually. Okay. And based on this, the TP, FE, and FN and TN, there are other metrics which can be used to find out the process monitoring algorithm. So that's a fault detection algorithm, fault detection rate, FDR, which is a function of again a TP plus, and FN, and false alarm rate. Because whenever you come up with the sum of your process monitoring algorithm, we need to have a very high fault detection rate and with the minimum false alarm rate. So, and also sometimes you use the F1 score to find out the efficacy of the fault detection. This is a commonly used, so I don't have to go in detail there. Okay. And now, general process monitoring scheme, it could be model-based, by the way. So that's one classification which you will be usually done. Whenever you are process monitoring, basically is a model-based and a data-driven based it is used. But model-based, yes, we have little difficulty because for a complex plant, developing a model, first principle approach model is going to be very difficult, and it may not be the model which you developed may not be truly representing the real system. So in that case, you will not have a good response from your model itself. So the what best way is that since we have too many sensors in the plant, so why don't you collect the data and then come up with some kind of data-driven model and then predict as and when the data comes, the new data comes, predict the output and compare with the measured outputs and then calculate the error. That's basically the residue. So based on the residue information, you're taking the decision whether is there any fault in the value of a sensor, or actuator. That's a basic idea of this. Now, there are different strategies which is used to come up with that. My case study, which actually goes with two case study I've taken. So one is that wastewater treatment plant. Another one is that both are the benchmark, well-established, well-accepted benchmark example in the chemical engineering domains. Wastewater treatment plant, we know it's a very important part of the municipal treatment plant. And another one is the Tennessee Eastman process, that's the TEP process. So some of the, whenever you come up with some new techniques, usually we try to test it on these kind of benchmark setters. And then, so that's a result which I'm going to show to you, okay? Now, being a chemical engineer, we don't have to discuss much on this, what is wastewater treatment plant, because this data which I collected from this, the cost that the European cooperative in the field of scientific, and they developed it, and then the data is available online. Anybody can get this data and this. The schematic representation of biological phenomena in the WTP represent in the same figure, same paper, which I have highlighted here. You can go back, you can go to this paper, which is nicely described this how this wastewater treatment plant actually performs and all those things. Okay. So basically, we why this is particularly important. Just have just given a there's a need for continuously monitoring the wastewater treatment plant to maximize the plant efficiency, because we need to continuously monitor what is the substrate concentration, what is the nitrogen concentration, what is the dissolved oxygen, because we want to increase the efficiency of the wastewater treatment plant. So that means we need to continuously monitor this particular plant since it is a very unstable and completely time varying, and because the load keep on changes. Morning for a WTP, the load is different, and the evening is different. The daytime the temperature is different. The nighttime temperature is different, because it's a highly nonlinear plant which actually operates continuously throughout 24 hours. So since it's a complex setup, needs to be monitored continuously in order to any possible faults that may occur. When I say faults, I'm only concerned with this. In this lecture, I'm only concerned with the sensor faults, which will be looking into this. So again, referring to the same paper, which is defined, these are the variables which is defined, and then simulation is carried out under 3 different operating conditions, and one is that a dry operating condition, a different operating condition, that's the dry data, storm data, and the rainy data, because there's a seasonal variation. So I worked in this. I would taken the data of dry data and then started developing a model. And before getting the data itself, the data length around, I think, 10,000 data points, and really looked into this data. So what is this actually basically, which gives that, if you look at the data, this is a violin plot basically. So what is the violin plot? So basically, if you look at the data set, it's a violin, width of the violin at a different x-axis. You can see that it doesn't follow the Gaussian in nature. It doesn't follow the Gaussian nature or a normal distribution or a Gaussian distribution. So this exactly clearly says that this follows a non-Gaussian in nature, that we need to do something else. So the very useful plot this is basically. So whenever you get the data, so we need to look into the data carefully and then how it actually behaves, whether it follows a Gaussian distribution, whether it's non-Gaussian distribution, because when it doesn't follow a Gaussian distribution, then just different techniques you must follow. Okay. And so that means the data which comes from the WWTP, which doesn't follow the normal distribution. So here is one more statistical method which can give us some insight about this data, the correlation matrix, which we are familiar with that. You can just get this. How would this actually, each variable actually related with this? You can say that, right? So, for example, there is a very strong correlation in the SS and the SNH. So, what exactly means the physical interpretation also can be.
I have one question.
Yes.
This previous slide, what you showed, you had got certain set of data, and from that
Yes.
you plotted these things. You plotted, you built a model for it. That is nothing but an equation where you substituted and you got it, or it was just a plot to predict something. That is one question. Second question is, if it is not, I understand Gaussian curve, if it follows that, that would be the best or well accepted one. But if it is not following, why
Yes,
it is a big concern, and what is the alternative?
Yeah. Okay, now the data which is taken, so the normalized rates, that basically zero mean, I've taken it and directly plotted the violin plot. I not used the equations. I just construct the violin plot and then try to see this. And then I can also plot the density plot. Also, it gives an idea about whether it follows the Gaussian or non-Gaussian. That's another technique. What is the magnitude of the non-Gaussianity also can be evaluated using kurtosis parameter can be used. Skewness can be used. But in this case, just I wanted to give that, yes, this data doesn't follow the non-Gaussian. That's the reason which, because why the issue is that, then later I'm going to explain it, because I use some kind of principal component analysis for this fault detection strategy. Then principal component analysis based technique, I use a t-square and SP statistics. So that assumption is that when I use those statistics, that basically assumes that the residue follows the Gaussian distribution. Then we will have a problem because then statistics, whatever I use, may not perform well for non-Gaussian data. That's the one reason. Is that okay?
Okay, okay.
Okay, thank you so much. So again, this I was giving the heat map of the correlation matrix of the data set. Again, I have taken this just to give an insight about the data set, because whenever you take the data, just try to analyze the data itself before even using a machine learning algorithm. That's very important because that gives which variable plays important role, how it's related, and what is the importance of that. For example, in this case, if you see that SS and I very high correlation, that's a positive correlation. All you can see that's all positive correlations. So that you can get some physical insight about this. So similarly, there are other correlations, XBH and XS. So you can go this, that's all chemical engineering terminology, which is can be understood easily. And this again not required because same thing. So as I said, the density plot also can give you an idea about this, how it actually, because it's no more a Gaussian. You can clearly see that it's not a Gaussian. So all the variables I just plotted and
Sir, what is the size of the data set here?
It's around, I think around 4,500 data set.
Okay.
Okay, so this is actually recent publication showers, this which he published in the Environmental Science Research and Technology. So this same work, I'm just presenting it. So with my co-worker. So basically it's schematic diagram, which I let me present it first. So how we actually are going to do this process monitoring, that should be clear before even getting in this. So as and when the offline data, if you get it, you pre-process the data. Basically, if there is any missing data, if there is an outlier, so you'll have to carefully look into this data and then pre-process data means in this case, I can think about as a converting into zero mean unit variance. So why do you do this? Because you're trying to give equal importance to all the features, all the inputs. Then you perform some kind of, in this case, I use the PCA model, principal component analysis model, and then using this PCA model, this means I going to only use the training data. That means I develop a training data, I use the training data, develop a PCA model, and then compute the residue. And I develop a Kolmogorov statistics, Smirnov statistics, and then compute the threshold based on the desired significance level. That means this step is a very crucial step. So this all happens in the training stage. That means this is a pre-processing stage and this is developing a machine learning model. And then as well as this is a step which is very important. We need to evaluate the statistics. And then based on the statistics, you'll have to calculate the threshold. What is the threshold? Now, once you threshold that, this part is done. Then as and when the online stage, you get the data set. So that means, again, you'll have to go through the same process, pre-process the data because we'll have to make it a zero mean unit variance and the generated residue using the PCA model. I'm not going to, just PCA model is already developed. So just using the developed PCA model, generate the residue and then evaluate the case statistics. Now, this case statistics, whatever you get it from the testing data set, you can call it as a testing data set or online stage data set. It'll be compared with the threshold value which you obtained in the training stage. If it is within the bound, there's no fault. And if it's yes, you'll have to declare the fault. So that means, so it's a very simple strategy. Basically, what we do, let me repeat once again, that's pre-processed data and develop some kind of a model, which you can think about a PCA model in this case. And since I gone with the PCA model, because a PCA model, even though it's a Gaussian data, I gone with the PCA model, but then PCA based statistics is going to fail to predict the fault. And then what I've done is that instead of normal statistics, I use for a case statistics and then use that for this. Okay. Just a brief introduction of the PCA. Because running out of time. So let's well-known dimension reduction techniques. So basically transform the large number of variables into very few new set of variables called the principal components. But physical significance is lost while transforming it, and you'll have to be a little careful while transforming the variables or reducing dimensions such that you should not lose the informations. So at least 95% of the information should be retained. So there are some methods to retain the number of principal components, right? So that is well-developed techniques
Sir,
also
sorry
available.
to interrupt, sir. Sorry to interrupt. We have another 15 minutes time for this session.
Okay.
Thank you.
The first principal components account for the most possible variation. That means basically is when you develop a when you perform the principal components, so you perform a PC and develop all the principal components, and then the first principal component which actually captures the maximum variance. So that means it is in a descending order. So how much principal components you want to retain based on your importance. That means basically, usually you go for 95% to 99% information you want to retain. The rest of the 5%, you may think about the noise in the data. That's how it is done. So there are drawbacks as well as advantage, because you're dealing with a very low number of dimensions, and then machine learning algorithms become much faster. Low interpretability of a principle, that doesn't give a physical significance. The trade-off between the information loss and damage reduction, that is a little bit careful. So that is how this algorithm is done. So I think if you go to MATLAB or Python, so there's a one command which actually directly can give the all the principal components for a given data set. Okay, I think in MATLAB it is a PCA. Python, I don't know, but exactly that's it. Sorry. So yeah, this is what is actually the fault detection's PCA-based model, and then PCA-based statistics can be used. For example, we have a perform the PCA and then build a PCA model, calculate the confidence limits for a t-square and SP statistics. When a new data comes, analyze the new data and calculate the t-square and Q statistics, and you compare with the training confidence limit. So that means if it goes above, declare as a fault, and no. Now, Watling t-square statistics used in PCA as well as the Q statistics. Or yes.
What is this threshold limit, or this some limit what you are speaking about, and how do you get limit? Is this limit is that the value is insensible or something in that order, or whether it cannot be used further? So I want a clarity on what is this threshold or this limit that you are speaking in the third step.
Yes, exactly. So once you develop a PCA model, build a PCA model. From the PCA model, we'll have to calculate the t-square statistics in alpha or a SP statistics. Now, these statistics, we need to evaluate the confidence based on the confidence limit. You'll have to calculate the threshold. Sometimes you can use the 3 sigma. It can be used. Sometimes you can use kernel density estimation. Also can be used to evaluate the threshold value. Basically, what you are saying that what I mean threshold is that statistics which within the normal operating point. So that is that threshold value basically says that yes, the t-square statistics or SP statistics, it's under normal operating conditions. It is if it goes beyond that, then you are going to declare as a fault. Now, as I've shown these equations on the left-hand side, there are 2 equations. Now, there is 2 things which is how would actually effect of using a t-square and Q statistics as a fault detection indices. Now, if you look at this one, there is in this particular figure, there is a 2 fault scenario which I represent. One is a hollow circle and another is the red circle. Okay. Hollow circle, the fault, which is on this mouse, you can see that, which is detected by both the statistics, Q statistics, as well as the t-square statistics, because it goes beyond the threshold, right? You can outside the threshold. So whereas in the case of other solid red fault line, that the statistics which falls here, which is not detected by the t-square, but is well detected by the Q statistics, because t-square statistics usually takes care of the normal operating condition. Usually the limit for that normal operating condition is much higher, or a confidence limit is much higher, whereas in the Q statistics, the limit will be less. That's one of the reasons it is Q statistics will be able to detect. But it's also sensitive to the any changes in the variations. So that is one. Now, since these t-square statistics and Q statistics actually assumes that it's a normal Gaussian distribution. So that is why we used K statistics in this case. So I just rushed this now. So this again, I'll not get into the math part of it. So this is already done. And now if you plot this, in this case, I have just shown that the 3 PCs have been used out of 8 variables. Only the 3 PCs, that means principal component, is used, and evaluate the K statistics, and then threshold is calculated and this. Now, the question is asked, what is the threshold value, which is for a t-square and SP statistics, and also we are compared with the Kisim chart, cumulative sum chart, and also the PCA-K chart. I've taken, there's the one drift and aging faults. So that is usually the common in the case of sensor fault detections. The fault can suddenly abrupt value can give. So that's we consider as, we can look at it as a drift fault. Then we know that the sensor over time is actually degrades. So its values also, its performance started decreasing. That's we consider as a aging fault. So now if you look at this first plot on the left-hand side, so that all the results which are shown PCAP square and PCSP statistics and PCAQ sim and then PCAKs. Out of this, the PCK is actually the performance better compared to this because the PCA SP statistics and T-square studies actually they failed to capture the or identify the fault itself. Yes, PCA Kisim chart able to, but it takes a longer time because it has to get the memory in that, then only it's able to this. So once, because there is so much of lag in this, the fault has actually happened as a 320 samples, but it's a PCA Kisim chart is actually detected almost close to 400 samples. So that is a little risky. Similarly, aging fault, also you can see that the PCA-based T-square and SP statistics is actually failed. Yes, SP statistics is able to detect after a long time. Basically. That is because the magnitude is started increasing, and whereas the PCA-based case statistics is able to predict very quickly, and then it's able to say that yes, fault has been occurred in the particular sensor. Okay, so this is the statistics which I talked about for both bias fault and aging fault, which I shown here. So that means that's a fault detection rate and false alarm rate. So fault detection rate when it comes to PCA is much higher. They should be close to 100. And you can say that it's a very close to value, very high value as a fault detection rate in both the cases, whereas the false alarm rate is almost 0. So where other techniques always use a false alarm rate. So that's always, you'll have to minimize the false alarm rate because we cannot take action for a false alarm, right? So that is a little dangerous. So similarly, F1 score is the second example, which I think I'll stop at this point. I think I can go to the conclusion because already only 5 minutes are left. And in case if there is any questions, I can attend that. And sorry for taking long and then not able to finish it early. So this one also, Tennessee man problem is also benchmark problems. So this is also available in this, which is it's used for even a control study as well as a fault detection diagnosis study, which is you can find it in this complete details of this particular description of the plant as well as the data set available and all those things we can get it. And so the process measurement is at 22, composition measurement 19, we have manipulated variables 12, and different fault scenarios are actually presented in this particular paper. You can download these different fault scenarios and then you can work on this here. It's a very useful data set which can be tested on your any new algorithm. So again, I'll not get into this. So I just so here I just presented ICA model, independent component analysis model, which is that the math part again, I just skip it and then I think I can go directly to this. No, yes. Yeah, the result which I shown that here again, this also is follows a non-Gaussian data. Again, I used PCA-based contour distance. Basically, I used the technique, statistics, contour distance. I used it, and then we found that its performance is better in this case. So I see basically it's used for, again, dimension reduction as well as model development. There's a slight difference between IC and PCA. So this is different statistics. And then, okay, so let me come to the conclusion. Sorry for not giving a good amount of time for a tendency estimate process. So the conclusion is that we are witnessing a new transformative era in the acquisition because you're going to get a huge amount of data set. The modeling approach have been increased, improved utilizations and management of different kinds of knowledge, AI to play a greater role in chemical engineering. There's a strong growing interest in machine learning among chemical engineers. On the flip side of this popularity is that risk of misusing machine learning or misinterpreting the black box results, which can potentially lead to a distrust about machine learning within the chemical engineering community, because blindly using a machine learning may not give a good results. High quality data and open source models encourage a researcher to use machine learning as a tool and grant them the ability to focus on their topic rather than programming. Although chemical engineers typically have a very strong mathematical and modeling skills, understand the computer science behind the graphical interface is a prerequisite for any model. So with this, I'll close this. Any questions? I'll be very happy to answer.
Yeah. The participants, yeah, still we have some time. We can ask questions.
Hey.
Somebody has to mute it.
Yes, I am checking.
I think I don't know.
Yeah, I disabled it. Yeah.
Okay.
Sir, I have a question. This models that you mentioned, you told that the models are not basically done there. And you told about this PCA model.
Yes,
and
sir.
also maybe about some other like other models also. Now, how do we select this model, PCA model, or if it is in case for water treatment and
Okay. So
water?
basically, it's what is your purpose, basically? So first thing is that what is your purpose for developing a model is a place important role. Whether you are using it for a predictive modeling, whether it is used for design of controllers, whether you're using it for fault detections. Now, when you're using it for predicting, yes, you can use it always directly. You need to have the labeled data, right? So you'll have to be very clear about what is your purpose, whether you want to use predicting some compositions, whether are you using it for some classification, or that means fault detection or a monitoring purpose, or are you developing a control design? That you should be very clear about that. Now, once it's done, if you are doing with the predictive model, yes, you need to have a labeled data. And for a fault detection also, for some monitoring, you can deal with the labeled data, but then you'll go with the classification algorithm. So there are different classification algorithms which can be talked about that. Basically, supervised learning algorithm also can be used. Now, if you don't know, if you don't want to do this, you just directly go for a unsupervised learning algorithms, which you get the data. So when based on the history, you just come up with some kind of a model, which the model is used to.
But that just come up with one kind of a model, that equation should be given by us now.
Yes, that is there. Yeah, PCA model, there is a set of equations.
Challenge.
It is not challenging. Mathematics already developed most of things. That's what I said. Algorithm is already well established in mathematics. That's not an issue. So being in a chemical engineer, we are good at maths somewhat. So it's not that bad because we study good amount of maths to be chemical engineers. So maths is supporting maths is there already. And even the optimization algorithm also is there for that now. So little bit of optimization methods, if you have knowledge, then modeling structure, then much easier. And of course, little bit of probability and statistics plays important role when you especially apply for when you're using a machine learning algorithm. That plays important. Little bit of probability and statistics, which will help us a lot.
Okay, okay. That means you are telling if you have input and output, and if you want to predict anything, PCA model should be the best one.
I'm not saying that. You can, we have many other models. Support vector regression is there. You can think about start with predicting. Linear regression model itself might give a better result. Linear regression.
Okay.
If it's just saying that y is equal to theta naught plus theta 1 x1 plus theta 2 x2, might give a better result. So why don't you start with a very simple model? Yeah, depend on the applications, what you're looking for.
Okay. Thank you, sir.
But by the way, predictive model, PCA cannot be used. It is a PLS model is used, usually. PCR or PLS, partially square, based on the, again, principle of PCA.
Okay. Thank you, sir.
Yeah.
Any more question? I think, okay. The
Yeah.
chat box.
Chat box, let me check.
Yeah.
I can see now. How to write a code for fault detection in WSD. Yeah, that's how to calculate cross validation error. Yeah. There was a question. I think I answered cross validation error. How do you evaluate? That is same mean square error only. Mean square error only. Basically, only thing is you're taking the different data set, cross validation data set of the input side, and finding the y-hat for the cross validation data set, and then defining the difference between the y-hat and y, and then multiplied with the 1/2m. That's a cross validation error. Like exactly looks like a MSC mean square error. And how to write a code for fault detection in WSN. I think you mean WWTP, wastewater treatment plant, using a deep learning. Yeah, you can come up with a deep learning, how to write a code. So now what is actually, say, if you are familiar with the Python, so there is already code is available for deep learning. There are some ANN code is already available. You can just pick that and make use of it. You just give the input and you'll be able to get the model directly. And if you're using a MATLAB, there's very simple. The MATLAB app is there now. So it's the latest MATLAB versions. All the different types of many apps are there. Machine learning apps and optimization apps and all those things can be made. That very simple. You don't have to worry much about. That's what the problem is, that if you try to use that model, then the interpretation of the results, it will be a little difficult if you don't know how it works. So you can use it directly without writing the code. Writing a code for a deep learning is a little difficult for beginners. It's difficult because we'll have to use back propagation algorithm and all those things. It's a little challenging. I think better to use inbuilt functions, because many people have donated in Python itself. There's a very nice routine is available.
Okay.
I think I answered that questions. I hope I answered that.
I think, yeah. Is there any more questions? Yeah.
Okay.
Okay.
So
There's no more
if there are
questions.
no questions, then we can close the session by thanking Dr. Muddu Madakyaru. Sir, it's very informative, and we started from the very basics of machine learning and give fundamentals, and also explain how we can use these in chemical process control with a case study. It was a wonderful lecture and very informative. Thank you very much for your time and sharing knowledge with us.
Yes, sir.
Thank you so much, Dr.
Yeah.
Thank you.
We look
Thank
for
you so
another
much,
opportunity to have you in person, sir.
Yeah.
Sure.
Okay.
I'll be happy to be there. And thank you so much, Dr. Rajesh, Dr. Nalin Kant, give me this opportunity. It's a lovely opportunity to be part of the SSN. Thank you so much. All the best for the next lectures. I'm sure the next lectures will have industrial participant. They might give a they might give more on how actually the real implementation might be happening in the industry. Sure.
Yes.
Thank you so much.
Thank
Thank
you,
you,
sir.
sir.
Thanks a
Have a good
lot.
day.
Thanks a lot. You have a good evening. Good night.
Good night.
So,
Yeah, dear participants, in another 5 minutes, we'll start the next session. I'm going to share the feedback form. Meanwhile, you can fill the feedback for the Dr. Muddu Madakyaru.
You can get the link both in the chat as well as in the group, WhatsApp groups also.
Yeah. Nalin Khan, sir. Yeah.
Yes, sir. Private, sir.
Sir, Rajesh, sir, can we fill the form after the next session together? Is it possible,
Yeah,
sir?
yeah.
Yeah, you can
You
fill
can
it. I
do,
mean, it
sir.
takes
You
only
can
1
do,
minute.
sir.
So,
Yeah.
Okay. So I'll fill the form after the next session. Maybe
Okay.
together.
No
sure,
problem.
sure.
Thank you.
It's the drop down, same link only, sir, for both
Yeah,
the
yeah, that's
things.
fine.
Okay. Yeah.
That's very fine.
Sudhakar, are you there?
I think he's there, but
He's having
there.
some issue with
Yes.
the mic.
Mike, I think, yeah, is muted.
Hello, can you hear me?
Yeah.
Yes, I can hear you.
Yeah, some issues with my office laptop. I don't know why I'm not able to turn on the mic and the speakers. So I'm not able to
Okay.
hear and not able to speak also there. So
Uh,
that's why I tried to connect from the mobile.
Okay.
Can you share your presentation, Sudha?
Yeah, I'm trying that. Did you give me the option to present? I'm not getting option to share my screen.
You joined with another account, huh? Okay, let me check.
Yeah, you check Sudhakar Katariya Sudhadidi. I joined with personal email ID. I have some
Yes.
restrictions.
There are two things. There are two.
Yeah, there are two Sudhakar Kataris are there. So,
Yeah.
can you check now?
Not the Qatari Kama Sudhakar, that is office one.
Yes. Now just now I made you as a
The one
presenter.
bracket external is the one which.
Yeah.
Now you should be able to present.
See. 1 second, let me open